Okay, our presenters today are Kurt Schmelzer and Tom Marsh. Kurt has 24 years of experience in process control, with the majority of his time spent in boiler, combustion, and energy. For the past 16 years, he's engineered customer solutions, managed projects, and currently serves as one of our combustion engineers. Tom Marsh has 25 years of experience in process control, with the majority of his time spent in boiler, combustion, and energy. He has experience across all facets of combustion and burner management. Kurt and Tom work together as energy consultants, working with customers to optimize steam-generating assets and process control loops. So welcome, guys. Thanks for being here and sharing your insights with us. I'm going to turn it over to Tom Marsh now.
All right, Robert, thank you very much. Well, I'd like to welcome everybody to our little virtual office here. I would offer you all a cup of coffee, but I can't really figure out which button to hit to do that. So I guess I'll just go ahead and get started. You can see today's agenda. We're going to talk about combustion curves and combustion setup, and then we're going to go through optimizing your flue gas oxygen control, and then we're going to review loop tuning and how you can coordinate loop tuning. And then Kurt's going to come back and talk a little bit about drum level control and best practices there. And then ultimately we'll go over keys to a successful boiler controls upgrade project. So combustion curve setup. This is one of our favorite things to do. When people talk tuning a boiler, think of the combustion curve setup. I think that's the most common aspect of the tuning that we do. It's the true heart of the combustion process. People often ask us, well, when should we do our combustion curves, or why should we do our combustion curves? And I think the most common explanation of that, or the most common reason, is for operational changes. You're looking at your O2 trim output, and you realize that output is at one of its boundaries. It's either too high or it's too low, and it's always maxed out, and that's clearly a sign that your curves, your fuel air curves, are not set up correctly, O2 being the feedback for the fuel air characterization. Or the operator is running at a bias. Inevitably, if the operator is biasing the O2, then there's something about the curve he doesn't like. Oftentimes there'll be one particular place where the O2 gets low. He'll bias it up so that he'll bias up the whole curve so that he doesn't run into that low spot. And ultimately, if the O2 needs to be at a higher set point, then the curve should really be redone so that the O2 controls there. And then, of course, more common things like mechanical wear. Something's happened to the damper drive. You've installed new drives or new valves. Maybe you're implementing your cross-metered system, so if this is the first time that you've actually set up the combustion curves. Or any other reason that you may be trying to promote fuel air mixing changes. Maybe your burner guy has come out and adjusted burner settings. That would be a good time afterwards to run combustion curves, or during or while he's doing that. And then also recently, as part of the 40 CFR Part 63, the new Boiler Act, there is a requirement to do tune-ups, specifically on oil, biomass, and some small coal burners. And that's actually subpart, what is it, JJ, there's 6 J's in a row for the subpart of the 40 CFR Part 63 if you want to look that up. But it requires a burner inspection and repair, flame pattern adjustment, inspection of the air-to-fuel control ratio system, which is the fuel air curves that we're talking about, ultimately optimizing the CO. So as you can see, there's lots of reasons to do this. And ultimately, it's all about the fuel in the air. And I don't care if you're burning in a burner, on a stoker grate, or as you can see in our picture here, the 16-cylinder, 1,200 horsepower Bugatti Veyron. It's all about getting fuel to match the air. And we want to do it in a fully metered and cross-limited system. Now, that is not what you see on the screen now. What you see here is an old-style setup, what we would call a parallel system or a jack shaft system. You can see that there is one drive, the big silver box there on the screen, and then the gas valve is what the arrow is pointing to. So you link the air damper directly to the gas valve, and then that gas valve has a series of screws in it that you adjust so that as it turns and goes up in load, the boiler goes up in load, the screws are pressed in farther, giving you more gas flow. And this is analogous to, keeping the car analogy going, to a carburetor in a car. I had a 76 Cutlass Supreme that had a 4-barrel quadrajet carburetor, and it worked pretty well. I'm not saying it didn't work, but if the air filter got plugged or anything, big temperature changes, it would smoke and not run very well. And again, that comes back to it's just relying upon damper positions and shafting to keep everything in the right firing rate, as opposed to new engines today that use fuel injection, where they measure both the fuel and the air, set those set points so that they're always in the correct ratio, and then control the air and the fuel flows. And that's what we see here with some of these pictures. We have gas valves and air dampers. We have gas flow meters, air flow meters, and then ultimately the feedback for that is the O2 meters. And then this is not just gratuitous advertising on our part, although it is what it is. I also wanted to put these loops up here because many times when we're getting ready to do combustion tuning, people will say, what do we need to do to prepare? Well, the one thing I really insist on when I start combustion tuning is knowing that the O2 meter has been calibrated recently. There's nothing worse than ultimately you're setting your fuel and air curves up to make the O2 meter read the right value, and if you go through all of that and a week later the customer does his yearly PM on the O2 meter, changes the cell, and then you realize that we set the curves up to the wrong value. So that's probably the most important one, but I would say all of these readings here you see are important. Airflow meters and gas flow meters are important. And then the actual outputs or the final control elements are important as well, especially if you're going to be characterizing those outputs. And if you have a draft control loop or you have an ID fan controlling draft in the furnace, you're definitely going to want to characterize the output of the air damper. The feed forward to the draft loop is the air damper output, and if you don't characterize it at low loads, you'll get a lot of noise, and at high loads, you'll get slow response. So that's our fully metered system. We measure the airflows so that they always stay at the right values, even if temperature changes or pluggages occur or things like that. But we also cross-limit those things, and the whole idea of the cross-limiting is you always want air to lead the fuel. So the air set point is high limited with the actual fuel flow, and the fuel set point is low limited with the actual airflow. And that way, as the boiler goes up in load, the air has to go up before the fuel flow is allowed to come up, and then as the air comes down in load, the fuel flow has to come down before the airflow is allowed to come down in load. So that's the cross-limiting that takes place in this little box in the middle that we call the combustion ratio limiting. So that's where the high and low limiting is. And on some low NOx burners, they also require the reverse as well, because it isn't necessarily safe to run too air lean. If you get too much airflow, it could cause disturbances in the burner and unstable flame. So sometimes on low NOx burners, they require the reverse as well. So ultimately, when we talk about characterizing the fuel and air, we have to use a characterizer block or a function generator, signal characterizer. I'm representing that here with an f of x, so it's an input to output relationship. And traditionally, this is where we would put the f of x blocks, characterizing the inputs for both the air and the fuel. Some people would put them on the set points, which also works. So you can characterize the set point coming from the demand so that the set point to the airflow and the fuel flow are matching. And then ultimately, if you want to characterize the outputs as well, then you have to put function generators on those outputs. And again, that's, the advantage to that is if you fully characterize it, the input and the output, if you're at 40% boiler load, you look at your PV on your air damper, it'll be at 40%, the set point will be at 40%, and the output will be at 40%. And likewise with the fuel damper. So it makes it very easy for the operator to look and know if there's something wrong or if somebody's not controlling the way he should be. So, all right, so here we go. This big scary looking guy shows up at your doorstep. and he says, all right, I'm ready to tune your boiler. He's got his little combustion analyzer there in his hand, and what do you want to do? Well, like we characterizers in your particular configuration and make sure we understand where those are. So that tells us what data we need to collect. We're going to verify with you that you've at least calibrated the O2 meter and hopefully other things as well. We're going to set up the data sheet, again, based upon where the characterizers are, and so that we have data as a result of our testing that we can turn over to you at the end to document what we did. We want to determine a grid location for O2 points. There's typically a single O2 meter. There may be more than that, but there's never as many O2 meters as you usually have combustion zones. On a multi-burner boiler, there could be many different combustion zones. So we like to see an O2 grid, or at least an O2 traverse across the back end, so that we get a better understanding of what the average O2 is across the entire plenum, and then we can use that to adjust our O2 set point to give you representative O2. We're going to want to talk to you about. So then when we collect the data, this is what our data sheet often looks like. This is from a test that I ran for one of our customers that had a 6-burner coal-fired unit. So these are the collection of the data that we collect. You can see the air characterizer input about halfway down the page on the left there. So this is what comes into the air characterizer, and then what goes out should represent what the boiler master is currently operating at. And then there's a little load curve off to the right that I use to track what the actual load is versus the boiler master. In the case of a new boiler, you probably know what you want your boiler master ultimate range to be set up for. In the case of an older boiler, you may have to determine that. Boiler master can't necessarily just be set 0 to 100%, where 100% equals MCR, or maximum continuous % load, to achieve MCR. You have to have some room for overfiring. Boilers typically have a 10%, 110% guarantee. So you have to set that boiler master up accordingly, and that's why I use this chart on this page. As I'm collecting the data, I can get the line and see where my boiler master is going to reach full load steam flow. And then here's a data sheet that shows the collection of the O2 test data. Burner boiler, we had 6 different ports in the O2 grid in the back end. Port 1 is on the west side, port 6 is on the right side, or on the east side. Probe 1 is the shortest, so that represents the top burners. Probe 3 is the longest, that represents the bottom burners. And as you can see, as we went through the data, we had some low O2 spots, so like 5.3 on the first run of data, we had a 1.54% O2 and over a thou. So we adjusted that, and you can see on the next curve, the next set of data, as we adjusted air shrouds, we were able to get those O2s and then the COs down. So that's that data, and ultimately that data results in O2 curves, or I should say fuel air curves. Sometimes I just don't know which button makes everything work. There we go. The green one on top is like the initial curve that we started with, and the red one is the one we ended up using. And then we have the O2 curve. The upper left-hand corner shows the O2 curve. Again, the green one was the old one, or the initial starting point, and the red one is one we moved to. As you can see, we ended up with a lower O2 at the higher end that was consistent, but that gives them a little bit better efficiency at the high end. And then you can see some of the other characterization that we had to do. This particular unit had overfire dampers as well as zone disk dampers, the zone disk for each burner. So we had curves for those. So that's our example of this. At this time, I guess I'd like to turn it over to Kurt Schmelzer, who's going to talk about optimized flue gas O2 control.
Welcome, everybody. I'm going to dive right in here and take a look at some of the considerations for optimizing the flue gas O2 control on your combustion applications. So this first chart we're looking at, it's representative here, and I'm going to kind of highlight here. This green portion, everything inside this box here is what we consider to be ideal combustion zone. Inside that box, in your typical parallel position solution that Tom was pointing out, where it's all based on positions and linkages, you'll find that we tend to skew to this green area, giving away a fair amount of efficiency that's potentially available, just to keep it up in a safe zone where we know that there isn't going to be any issues due to changes in the air temperature or, you know, fouling or blocking a filter. To add an actual flue gas measurement allows us then to set up a control strategy where we can capture some of that efficiency and move back down closer to the stoichiometric point. And by the stoichiometric point, we're talking about the point where all the fuel is being completely combusted and there's no unburnt carbon chains left in your flue gas stream. And realistically, as you can see, I mean, this CO curve here would be the ideal and you would have 0 CO. Well, that's not actually achievable. This dotted line here represents more a realistic, due to poor mixing, what you would, or incomplete mixing, what you would see for your combustion. So as we're looking at an in situ O2 analyzer, the key becomes where do we place them and how many of them do we need? You may find that a typical package boiler, one is sufficient. We're talking about smaller ductwork, a single burner, not as many things to consider. As the boilers get more complicated or larger, multi-burner boilers, for example, we may find that we need 2 or maybe 6 to get a representative value to represent the actual content in the flue gas O2 that's being seen at the burner. As we get over on stoker fires, you may see 2 to 4. And when we start talking about balanced draft or an ID-FD fan boiler application, we need to be concerned about where within the furnace we are placing the O2 probes. Because as the furnace runs under negative pressure, leaking observation doors, man-way gaskets, those types of things, subblowing openings, all allow tramp air, uncombusted air, into that flue gas stream and can affect those readings. So typically moving the O2 sensors as close to the combustion zone as practical ends up being a good solution, especially in older, leakier boiler applications. Your limitation there is there is a temperature limit for a typical in situ O2 probe, and you have to ensure that you don't put your probe into a zone where you're going to sustain long-term damage. So once we have the O2 probe in place, then the key becomes on this next slide here, we're talking about how close to the knee can we operate. So this red arrow here is depicting kind of that optimal point. By the knee of the curve, we're talking about this CO curve as it comes down here makes this nice knee shape. Anything over here on the right-hand side of this curve is really considered to be a safe combustion zone. As you get down and you get lower and you start to see the CO spike, that's an indication of a very incomplete combustion, potentially even considered substoichiometric. So the idea is to set up your control strategies so that you can run right at this most optimal point. Some typical numbers we see for single burner would be somewhere in that 2.5 to 3.5 range. Pulverized coal, the numbers we'll typically see for a representative flue gas O2, we'll see that 3 to 3.5%. Stoker fire, there's a couple different varieties of stokers on the market today. The old traditional overthrow, we would typically see something in that 4 to 4.5%. And what we're seeing in applications where customers have upgraded to a newer underthrow with an air assist system that really helps with the fine coals, we're seeing the need to run at 5 to 5.5 to make sure that we have enough air underneath the grate to resolve issues with slagging and those types of things. Biomass fired, it's anywhere from a 4 to 6%, and a lot of that's going to depend very heavily on the air distribution. And the last one, just for an example, is the RDF fired on a stoker. So a refuse-derived fuel or a processed municipal waste. Typically, we need to see those above that 7%. And this isn't about efficiency at this point, this is a limitation based on the chemical reactions that will happen in the furnace if you drop down lower. The additional off gases off the solid waste actually can attack the metallurgy of the tubes within the furnace, and that's the concern there. So to get to that, we're concerned about some of the basic control loops on the boiler. The first two being the fuel and air highlighted there on this package boiler, and then the last one being the flue gas O2 to get to an O2 trim. We need to focus in on these loops. But ultimately, we also need to have a control strategy that provides us a single knob control. In other words, it's analogous to that accelerator pedal in your automobile or your car. Everyone knows if I push down, I'm going to go faster. If I let up, I'm going to go slower. We need that same thing for the steam production rate on our boiler control strategies. That's typically our boiler master. It may be our pressure controller in simpler applications. But typically that's considered to be a boiler master point. And that's that single point of, or single knob control where an operator can choose to change the firing rate and call for more steam or less steam. In this diagram, very similar to the one that Tom was showing earlier, the demand here is that single knob access point. That's from that boiler master, our combustion ratio limiting here. This couples then with our O2 trim control. In a true cross-metered strategy, then the O2 control is affecting the airflow set point through there, allowing us to set those curves up and move closer and closer to that optimal efficiency point. We move on over and then look at the stoker-fired control. The best way I can think of to explain the stoker-fired control is you need to think of it as like you're controlling a campfire, or maybe you're a blacksmith and you're controlling the hearth in your blacksmith shop. You give it more air, you get more heat. You give it less air, you get less heat. Your fuel essentially here is now setting out on the grate and is ready to combust. You have heat. All you need is air for combustion to release the energy and give you the heat. So in this case, the demand, or that single knob control, really ties to the airflow systems, which are a little more complicated, but yet we still have our oxygen trim loop in there that's trimming back our air to try to maintain us at that optimal point. There is no fuel flow measurement or direct fuel flow measurement, as you can see in this strategy. Once we get all this completed and we've done all the data collection Tom talked about, into this O2 curve, we end up having an O2 curve that looks like this. And our goal here is that the set point of our oxygen trim controller is going to vary as we change from 0 to 100% fuel flow, starting from higher numbers and then see how it drops. One of the key setup points we're looking for is that right along here, the lower we can maintain this minimum O2 level, the more we maximize the efficiency of the unit down at these lower load operating points. The key here, though, is not to lower this so low that we start to hit up and right up that knee of that CO curve on that first chart we looked at. So moving on, I'm going to hand this back over to Tom, and he's going to talk about the effects on loop tuning on these critical airflow and fuel flow loops.
Well, thank you, Kurt. So yeah, we get to talk about boiler loop tuning now. So we talked about setting up the set point curves for the air and the fuel so that they are always equal at load points, but then the question becomes, as we transition from one load to the other, we want that fuel-air ratio to also be equal at all load points, even during transition. So to do that, you really want to coordinate the tuning between the air and the fuel. And then the question becomes how to do that. Well, we find that the best way to do that, to coordinate tuning between different loops, is to use a lambda tuning method. Now, some people will tell you that, well, if we set the reset the same, won't it really be the same? Well, that's not the full that's not the full answer. The actual response of the loop is determined upon its first order characteristics. So you really need to model those characteristics before you can understand, how to close loop control. And that's what the Lambda method allows you to do. And so if you look here at the left-hand corner of the screen, the bottom here is some bump tests that were ran. In this case, we're using NTEC's collect tool. NTEC is a series of tools that allow you to do tuning applications on pretty much any platform. So you can see the bump tests that we did here in the bottom and the resulting PV changes in the top there. And then the NTEC tool allows you to use its curves to model those changes and then predict accurately the outcome. But truthfully, Lambda method is very simple to do. We most commonly do it with just whatever trending package you have available, and then using a spreadsheet to do the calculations. I've done it with as little as a stopwatch and a strip chart. So it really can be done on any system with just about minimal tools. And it, again, allows you through a very simple test where you just bump the output in manual, open loop, to collect data and characterize that open loop response so that you can then pick the closed loop response time that you want. All right, and I think we've just about slided you to death here. So we're going to try to go out into a virtual machine here and show you a demonstration. Now, of course, we're using Delta V as a system to demonstrate this. This could be any system, but of course, we use what tools we have available. So, Kurt, if you would take, say, the airflow loop, as you can see here, we have got the tuning set up on the airflow using just kind of a standard off-the-cuff number, 0.5 gain and 30 seconds reset. And we've also set the gas flow up that way. Those are numbers that we use as a default tuning in our standard for fuel and air. Kurt's going to give the boiler master a bump here. Kurt's pretty heavy-handed, so he'll probably just give us a 10% bump directly. And we see that the airflow and fuel flow set points go up. The top chart is the airflow. The middle chart is the fuel flow. And you see that those set points go up. But the actual process variables are a little bit slow to catch up. So 0.5 is probably not the best gain. 30 seconds may not be the best reset. I did want to point out the bottom trend there, the little green squiggle that you see in the bottom trend. We're using a calculated fuel-to-air ratio to represent what O2 would normally show you. Normally, if this were to happen and we were to have an offset between fuel and air, you would see an O2 change. Since this is a demonstration system, we're just calculating the fuel-to-air ratio and trending that so you can see that the fuel-to-air ratio wasn't very good. Now, it wasn't horrible, but it wasn't very good. And as you can also see, we're quite a ways away from getting the set point. So we could, at this point, put this loop in manual and bump test it using the manual controls. I think what Kurt's actually going to do is at least for one of them, he's going to go through and do an auto tuner. Okay. Now, Kurt, he's got lots of tricks. Okay, so he's got things in mind. So he's adjusted the reset of 1 to speed it up a little bit. Changing the firing rate. And now you can see that 1 is much faster, but that's not necessarily helping our green line that's down there. So let's see where Kurt takes us next. Okay, so here is a smart tuner that we have, part of the Delta V Insight package. So again, we could do this. We could do this with just on the charts and putting the loop in manual and bumping it. The smart tuner has a test button. You press the test button, and then it's going to take it through a 5%. That was the step size, the 5% step. And it's going to go up and down a few times, and it's going to come back and model that process and give you some tuning constant recommendations. So it's getting through. It's almost done. Now, I can tell you that as far as tuning method goes, the Lambda tuning method is pretty simple. It's pretty pretty easy to convince an operator that you want to put the loop in manual and move the output around a few percent. Most operators will let you do that. If you wanted to try to use a Ziegler-Nichols tuning method, the way you do that is you increase the gain until you take the loop right to the edge of stability, and then while the loop is oscillating back and forth, you measure the size of the oscillations and then the time width of the oscillations, and you can calculate tuning constants from them. But while an operator will normally allow you to take a loop into manual and move the output up and down a few percent, if you ask the operator, say, okay, can I take your loop right to the edge of stability so it oscillates like crazy, because that's the way I'm going to calculate your tuning constants, you're probably going to get thrown out of the control room. Okay. So Kurt, I think, have you updated both of them? Yes. And you're using lambda on both of them? And have you got them set for the same lambda time? Okay, so now they're set both for the same lambda time. So now as we do a bump test.
Okay, so based on the earlier bump test we ran, now we should have them both at the same lambda time. And we've got our 10% increase in firing rate. As you can see this time around, our green line isn't nearly as drastic as far as its deviation on the fuel-to-air ratio. And the two curves are coming up together. But I noticed, Tom, that they're going up the same rate.
Yeah, you know, normally in a boiler application out there are watching saying, Tom, we're going on an increase in load. I thought you said that the airflow is always going to lead, that the fuel flow is not going to go up until the airflow goes up. So why is our set point changing? Well, for the purposes of this tuning demo, we had the cross-limiting turned off. Now Kurt is going to change that. He is going to turn the cross-limiting back on. And now when he does a load change, well, still in the positive direction, you're going to see that the fuel is waiting for the airflow to go up. And that's our cross-limiting effect. So again, on the way up, the fuel waits on the air. On the way down, the air waits on the fuel.
And our green trace here is showing that we stay on the fuel lean side of that equation on the fuel-to-air ratio, but not too far on the lean side.
So again, coordinating the tuning of the two loops is very important. It helps it so that the boiler will stay at loads, at the right air-to-fuel ratio throughout all load ranges, and even during transitions.
And we'll see the opposite here on the load decrease.
Yeah, that worked pretty good. I was a little bit nervous about the virtual machine in this environment, but that was good. All right, so at this point, Kurt, I think I can turn it back over to you.
Okay, so the next subject we're going to talk about a little bit, spend some time on here, is the drum level control. And the key here is drum level control really is not going to gain you a lot of efficiency. It could affect your capacity if you have poor control of your drum level due to carryover and those types of issues. But also, ultimately, in my mind, it's really about your reliability. So, for example, ASME's code calls for 2 separate and independent drum level indicators on every steam drum. What we're showing here on this page on the left there is a multi-point system, which is a good separate independent indicator. It also can be used as a great solution for your high and your low water alarms, and even your high and your low water interlocks if those are required in your application. You can see on this particular graphic it's showing both a local display on the box there and then the option for a remote display that can show up in your control room. Typically these will be a series of red and green LEDs, green representing the water level, red representing the steam in the top of the drum. The other application that we're showing here on this page on the right side is a fairly typical installation for differential pressure level measurement. Some of the key issues here with this are the calibration of that transmitter cannot just be merely the span value of the distance between the two sensing taps. Because this environment right here is saturated steam, completely blanketed, and this is saturated water, we have a difference in density here than we would if this was air and just water. Therefore, we have to adjust our calibration here or compensate online continuously for the changes in density. So the issue you'll typically have as you get into higher and higher pressure applications, this level measurement will read in error when compared to this type up until you hit close to normal operating pressure. Some applications, what we're seeing today is the use of the guided wave radar. Now this is limited. This would be used in place of the differential pressure solution, but this is limited to steam temperatures that are within the range of what this device can handle. So it's not going to work well in many of the high pressure steam applications, but it is proving to be very reliable on these lower pressures. This particular application that we're showing a photograph here is a similar application, and that is a steam blanketed heat exchanger, so that we have the same level measurement challenge that we see in a steam drum. Moving on, once we have a good level measurement and we've addressed both having our two independent sources, now we need to talk about the drum level control. The most basic and simple drum level control is what we call single element. In single element, we have a level transmitter. That would either be a DP cell or guided wave radar. Never really recommend using the multi-point devices. The resolution on those will just cause you tuning nightmares because of the 1-inch change between each update and level. The level will have to move either a ½ inch or an inch depending on the spacing of the probes before you change the level. That really causes some problems in the tuning and response of this loop. So we have a level controller, and then we have our final control element, a feed water control valve. In this case, one of the limitations here really is our lack of steam measurement. We have no way to anticipate needs or changes in feed water flow based on any type of change in the steam flow leaving the drum. The other challenge we have is we don't have any way to deal with or address upsets in feed water pressure, which ultimately will affect the flow through the control valve. So the next step then, as we move forward, would be to look at a two-element drum level control. As you can see in this one, we've actually added a flow transmitter onto the steam flow. This gives us a feed-forward capability, giving us two elements, level and steam flow, to use in our control strategy to help drive our valve. In this case, though, we still don't have any way to address upsets that we may see in feed water pressure due to changes in feed pumps. Maybe you have a multiple feed pump situation, or maybe you're a common header facility where you have a common feed water header and you have multiple boilers drawing off of the same set of feed pumps. Those are all cases where this particular strategy ends up falling a little short, and we see more challenges with consistent drum level control. Then the ultimate then, and the end all, would be to add a three-element control. Now, as three-element control works pretty good. We have the steam flow. You notice we've added another controller for feed water flow, and we have a feed water flow transmitter. This allows us to address those upsets in the feed water flow side of things. It also allows us to address things like shrink-swell phenomenon due to increases in steam flow, and sometimes firing rate. One of the key things, though, in any robust three-element control strategy is addressing how this strategy reacts under failures of either of these flow transmitters or the level transmitters. What we typically like to see is that a failure of the steam flow transmitter would shed this back to our first slide in these control strategies, back to a single element control strategy. That's also having a strategy that switches between single and three is also very useful in those low load, no load conditions when you're first starting up a boiler or you're starting to take a boiler offline. That single element's going to do a better job and allow the operator to leave the drum level control in an automatic mode instead of having to watch the level and manage the valve and the flow of feed water on his own. The second failure to be concerned about, though, is this feed water flow transmitter. And in that case, we typically reject back to a single element mode as well. However, you could choose to go into a 2-element control, just ignoring the feed water flow loop. So the next topic we've got, we'll spend a little time talking about the elements to be successful. Once you've identified that you have the needs to do a controls upgrade project on your boiler controls, to me, the very first thing starts with an effective project execution process. And I like to view it as a process. We use it as a process. The project really starts, for me, in this define and approve phase right here. This is where something's been identified. There's an opportunity to either improve the reliability, improve efficiency, maybe it's to regain lost capacity out of the unit. It's in this stage where the scope gets developed and approved, and typically a budget gets estimated for the project. The next phase of the project then is where we get into the design of exactly what the complete and final solution would look like. What final control elements may need to be addressed, what instruments and measurements need to be addressed, what type of control strategies will be deployed. This is then followed by the engineering phase of the project. This is where we typically see the instrument spec sheets get developed, control valves or final control elements may be sized properly, and installation details worked out for how they can install properly on the boiler. This is where the control strategies go from the requirements phase into a working configuration, whether that's in a DCS system or that's in some other type of control hardware platform. This is then followed by the installation phase. This is where essentially the hardware meets the field. This is where things get installed. We get things installed, checked out, and then we move into the startup phase where we go through the commissioning of the new controls, any new instruments, calibration verifications. We get into tuning, adjustments of combustion curves, and then ultimately we go back to operate. We view this kind of as a complete cycle because after you operate, you need to maintain, and there's certain, like the periodic combustion curve tests that we talked about in the maintain cycle, and out of those may come more opportunities identified where you can optimize. And if you identify limitations that are keeping you from being where you want to be optimal, that's how we view the project execution cycle. So in the boiler control arena, it really starts at the boiler. And the key to a successful boiler control upgrade project in our experience has been addressing the final control elements and the measurements. And in this slide, we're looking at a couple actual installations that were worked on recently. In this case, this was a stoker-fired unit, and we're dealing with an overfire air. And this is an actual new airflow measurement was installed. And then the lower set there are showing us an FD fan airflow measurement on the same unit. Once we get the airflow measurements being so critical, and typically having those at the inlet of the fans is preferred. I'll get the slide to change. There we go. Okay, and in this slide we're looking at the final control elements. We're looking for accurate, reliable devices. We want them to position accurately to the request from the control system. So on the left, the first one we have there is a rotary vane actuator that we've got installed on a damper application. The middle one, of course, we've got the Fisher control valve that we're accustomed to working with and using for, say, feed water or gas flow. And then over on the far right there, we're showing VFDs. And VFDs in boiler applications have proven to be very reliable and energy-saving application, and very responsive to the control, especially in the air. And flue gas evacuation, say an ID fan application. Follow this up, once we get it all put together, there's some minimum capabilities that we need to look for from the control platform. The first one for me is we typically need a control platform as we move from an analog world to a digital world potentially that is fast enough. I typically like to see a half-second scan rate on all the loops on the boiler. The second thing is in the world of digital final control elements, we're looking for accurate digital representation of the values from the good instruments that we've put out in the field. So we're looking for 32-bit floating point math on these. And the last aspect of doing, in my mind, a successful controls upgrade project is to think about the paradigm shift typically. And do we stay in the operating environment shown on the left with the classic bench board with lights, knobs, and chart recorders, or do we move to a paradigm on the right where operators are presented with information on flat panel LCD displays where they can manage the capital equipment assets and not spend all their time having to tweak the knobs and the dials to get what they need to keep things online and running. So the next step here is next steps. We have full bullet points for you to consider here. What we hear a lot is we may have already know where some of our opportunities are, and just looking for how to act on them would be a good next step. Potentially, maybe you believe you have opportunities and you're just not sure how to quantify them. So commissioning a steam generation audit where we may look at the measurements, the control, the final control elements. Maybe we need to review the burner management and the safety systems on the boiler. Maybe we need to evaluate the loop performance to determine whether or not there really is problems with measurements or final control elements. Also, we may need to assess the combustion performance. Are you unable to achieve the CO levels that you're expecting, or your original OEM tells you should be able to reach? Another area that we see in the boiler house typically may get ignored a little bit from time to time is your steam traps within your population around your headers and your steam distribution system tie-ins. Other cases, we've got evaluation of multi-boiler control coordination and control schemes, optimization of multi-fuel boiler operation. That can be tricky and a real time and money saver for your operators if done well. Particular to the pulverized coal, optimization and tuning of the pulverizer is something that tends to be ignored from my experience and can have a significant impact on your both operation, your responsiveness of your boiler, and your emissions. The other last item we have for your consideration would be maybe you need some help on how to develop a scope of work to tackle one of these opportunities you've identified, or maybe you even need some assistance on coming up with a justification. So, moving forward with this point, we can open it up for questions.
Okay, thanks, Kurt and Tom. Kurt and Tom are both available now to answer your questions. I would like to quickly apologize for some of the voice quality out there. We definitely have some improvements to make on our end. If there's something that you missed, please check on Novaspect.com's media page. This recording will be posted in the next few days. If there's something that you missed and you want to review, the recording probably caught it pretty well. So again, open up the lines here. You can use your control panel to raise your hand and we'll unmute your phone. You can also type a question in the Q&A area of your control panel. On your screen there, you'll see how to get a hold of Tom and Kurt at one of our locations. We have locations throughout the upper Midwest. You can hit Tom at tmarsh@novaspect.com, and you can hit Kurt at kschmelzer@novaspect.com, or you can talk to any of your Novaspect account managers. So as we're waiting for more questions, I just want to remind you all, please take our survey when you exit today. We're looking for 100% of those surveys to be filled out, if you don't mind. Okay, if there's no more questions, then that will conclude today's event. We hope you found it valuable, and join us for another Novaspect webinar down the road. And thanks for participating today. Have a great day.